Hi, I'm Victor Racicevic. This is Adam Wootton.
Yeah, I'm Adam. Hi.
And this is this week's lab video for Side 383 with Professor Andrew Tripp. Now, this week's lab is all about wind flow. Adam's actually going to describe it.
Yeah, so basically we're going to be going around campus using our wind flow measurement system device that we built last week. I wasn't there, so I didn't actually make this. And we are going to be measuring the wind speed and the wind direction at various points and try and come up with a flow map of how the wind is flowing through campus.
And the reason we're doing this video together is because we messed up and we accidentally picked the same day for a video. And that means that we have to do a Kenny versus Spenny style who can make the best video competition. That's you. Right, and I guess in the spirit of Kenny versus Spenny, we're just going to have a ridiculous rule, which is no cops. The reason this is because to get a picture of our flow map, our flow grid, we're going to need to climb onto stuff, and so I guess...
Right, so for this lab we're going to be walking around campus, and we're going to be using some highly scientific equipment that Nick will now demonstrate. So as you can see, we have a protractor here with a thing on it, and when we stand and hold it against the wind will blow this thing, and it'll reach a certain angle on the protractor, and in doing so we'll be able to measure the wind levels. Thank you, Nick, for that demonstration. We also have plastic bags because we do not have ribbons because we are poor. We are going to rip these plastic bags, tie them to wood, stick it in the ground, and build like a grid sort of thing with the wood and the plastic bags. And the idea being that we'll be able to map a sort of like a wind pattern throughout an area where the grid exists. So if we take a picture from above, we can see certain plastic bags being blown further than others. So we're between CPH and DWE. According to our handy dandy scientific measuring device, there is approximately not any wind whatsoever. So we're at the Poet's Patio. Still not that much wind. Well, we're beside RCH, and we seem to have found some wind. According to our measuring device, we've reached the first notch. So we've gone from the green over there to the top of these stairs to measure the difference when we go upstairs. And it seems that the wind is a comparable amount of strength, but for some reason it is going in the opposite direction. Very mysterious.
Following the curvature of the building.
So as you can see, we're between three different buildings in sort of a weird Y-type shape. Victor's in the shot for some reason. As per the building channels thing that Nick was talking about earlier, we were expecting to see some like wind cross channels mixing up in here, but nope, we don't. There's just nothing, again.
As per the Kenny versus Spenny spirit, needs to be a little bit of cheating involved, so I'm going to try to get Nick to interfere with Adam's videos a little bit. Yeah, see how this plays out.
So we're in the overpass between some buildings that we never go inside, and here's
Science
Nick.
Buildings.
Yes, science buildings. Here's Nick on the ground. He seems to have developed some sort of stroke. But, as you can see, there is actually wind in here. It's reached the furthest it's been since we started this experiment. It's just past the first notch. Isn't that right, Nick? Yeah. Here we are at the egg fountain. It would seem that there is about just as much wind here as there was everywhere else. That was a cop. We only had one rule.
There you go.
Alright, so we're at that thing that's close to E5, and Victor's messing with my scientific data here, but it seems that this is about the windiest place we've found so far. There's actually, as you can see, it just reached almost 2 notches there, so that's good. So we've migrated from down there to up here, and there is almost no wind. We think that's because, according to Bernoulli's equation, the height difference means that there's potential energy here, so the amount of wind flow is lower. Isn't that right, Nick?
Here's a simple diagram explaining what I meant by that.
Up here at the top of the hill where I just was, there was a smaller velocity than down here at the bottom of the hill. The reason for that is because, according to Bernoulli's equation, the potential energy of a flow and the kinetic energy of a flow add up to a constant. That means that when the potential energy is increased, the kinetic energy must be decreased. In the case of this hill, at the top of the hill there is more potential energy because the height is higher. According to this term, that means that the density of the air times the force of gravity times the height is equal to the potential energy. So the height here increases this term. That means that the velocity term must be lower. So the velocity at the top of the hill is less than the velocity at the bottom. As you travel down the hill, the velocity slowly increases. Isn't it fitting that the most wind we've seen all night is right at E5 where we go to class every day? Look at that, 4 notches. Wait, it's even reaching 5 notches. If we wait long enough, it could reach 6 notches. I don't know why my camera's blurry, but oh my god, look at that. Here we are, sitting in front of E5, making
How are we gonna do this?
making ribbony things
Like
out of.
obstacles.
Here you can see our grid system that we've set up in the train tracks. Hopefully a train doesn't come. So now that all of the flag things have been set up, there doesn't seem to be much wind here, so there aren't very useful results happening. Earlier we saw some movement on the flags that are more into the middle of the tracks, and we think that's because there's grass on every side that's blocking the wind. So the only way that the wind can flow is down the tracks like there and there. So maybe if it was a windier day, we would see these kind of going like in this direction or that direction. This can be explained using the following diagram. Around our flow map area we have a bunch of different grass squares which work together to create flow channels. So the wind is trying to go through these flow channels, but there's a no slip condition along the edges of the grass, so the velocity of the wind at the edge has to be 0. But then the velocity in the middle has to be the speed of the prevailing wind. So there's a velocity gradient where the speed of the velocity increases as it gets closer to the center of the channel. The different channels interact together and create this sort of turbulent flow area in the middle. So over here we have laminar flow, but as it transitions we end up having a turbulent flow here, and the different wind channels mix together and create even more turbulent flow in the middle. What that means is that the measuring sticks that we place near the center of the tracks, we're experiencing more wind and more turbulent flow than the ones that were closer to the grass, because due to the velocity gradient, the speed of the wind was lower closer to the grass. So here's the flow map that we generated based on the wind data we recorded while walking around campus. As you can see, the area with the highest wind speeds was near and next to EIT. This can be explained by the fact that narrower channels force the wind to move faster. If a certain mass of wind enters the channel in an open area, the same amount must leave at the other end. Therefore, the mass of air flowing through each cross-section of the channel must be constant. Since the cross-sections in narrow parts of the channel have less area, the velocity of the flow must be higher for the same mass flow rate to occur. This explains why the open area near the physics building has almost no flow, but the narrow channel in front of EIT has a lot. A similar effect is seen in front of E5, where the air coming from the open area to the south is forced through a comparatively narrow area, creating a higher velocity flow. The opposite effect is seen in the open area next to the physics building, where the channel is quite wide and therefore does not force the wind to move faster. As such, this was the least windy area observed during the experiment.